What's up, guys? Last week, Meta released their amazing global tree canopy height data at 1 meter resolution. In today's tutorial, I will show you how you can easily load part of this data into R and then create some powerful data visualizations. Alright guys, our first task is to install and then load the packages that we need. The first package that we need to install is the package DevTools, because we will need to install some of the packages from their GitHub repos. So that's the first one. The second one that we will need, if you don't already have it, is the package Pacman, which we will use then to install the remaining packages from CRAN and then also load them into this R session. Okay, so we're gonna start off by first of all installing the package CHM loader, which is gonna help us get the Meta and World Resources Institute data on a tree canopy height. So to install this one, we will call DevTools, and then we're gonna use install GitHub from this package. And then here we're gonna provide the location of this package. So that's the first one. The second one that we want to install, again using this DevTools install GitHub, is the development version of the leaflet package, which we will be using to create an interactive map with this data. So for that purpose, we'll be using this leaflet version. And again, you can run this and then also install. Now in this last stage, what we will do is take this Pacman package and then use the pload function from it, which is going to help us install the packages that are not already installed and then also load them. The first package that we want to actually load, because we already installed it, is this CHM loader package, which is going to help us fetch the data for any area we want on tree canopy height at 1 meters. The second one is the Terra package, which we will need to deal with raster files, since the one on tree canopy height is actually a raster file. The third package is the SF package, which is going to help us deal with shapefiles. And we will have here shapefiles because we also want to create a polygon of a bounding box for which we want to get the data. The fourth package is map tiles, because we do want to have the street view layer in the background. Then, of course, we will go on to creating the map itself. But before we create, we also want to define the breaks that we'll be using. And for that purpose, I like to use the classing package, which helps us get the natural intervals of our data. For the graphical parts of creating the map, we'll be using ggplot2 from the tidyverse umbrella package. Now, in order for us to actually incorporate this street view layer, we will need actually tidy Terra package to do that for us together in ggplot2. And of course, we need to also load the leaflet package, which is going to help us create the interactive map in R. And finally, to export this interactive map as an HTML file, we'll be using the HTML widgets package. And these are the packages and their versions that I just loaded together, also with their dependencies. Okay, so our first step will be to define the buffer for the area that we want to fetch the tree canopy data for. And the area for which I want to get data is Oslo. So here I'm going to type Oslo coordinates in Google search, type enter, and then the very first result will give you in decimal format latitude and longitude coordinates for Oslo. We will now copy these and then go back to R and continue our work. So back in R, we want to use these coordinates to create a buffer around them. It's going to be a smaller one of 2 kilometers. Turn it into a polygon, and later on we will use this to fetch data for this specific area. So first of all, let's define the latitude and longitude. As we said, the first value is latitude and the second value is longitude. Now the next step that we want to do here is use these to create, first of all, a point which is going to be an SF object. I'm going to create here city coords object, and then using SF package, I'm going to call st points here. Now here I need to pass these 2 arguments in a specific order. First of all, we need to pass longitude and then followed by latitude. Now that we have this, we need to tell R what is the actual coordinates reference system of this point. And over here, again, we can use for that purpose SF package and this specific function here. And then within this, we just pass the 432x6 datum of the WGS84 coordinates reference system. And then the very last step is to simply convert this into a buffer around these points So over here, a very cool thing about this st buffer function from the asset package is that you can actually set the units that you want and then also then define how much you want. As we said, we can go for like a smaller one because the data is quite big since we work with the tree canopy height at 1 meter resolution. So I'm just going to go for a buffer of 2 kilometers. In our next step, we can use the CHM loader package to get the data. This package actually can also be used to test how accurate metadata is against some other leader data, for example, but in this tutorial we'll be just using it to download the data. So I'm going to create an object here, and then I'm going to call the CHM loader and then download CHM. So this one actually accepts 2 arguments. The first argument is what you are actually gonna use. What is the area? So in our case, it's this city quartz area, so it's a polygon. And the second one is the file name argument, which is basically how are you gonna call this. So we can call this, for example, Oslo CHM, and then .tif. This is very important. Now, when you actually start this is going to take maybe a minute or maximum 2, depending on your internet speed, but not more than that. As the code successfully runs, you will see these 2 warning messages, but you can safely ignore them because they're not really errors, and we can continue with our work. The easiest way to expect this data is to actually plot it. So we can just use a from Terra package plot function, and then we can pass this newly created object, and we can also give it a certain color. So for example, we can use from base R HCL colors. We can use, for example, 64, let's say viridis for that purpose. And then once you run this, you will see the plots. And in this first rough version of the plots, you will notice that the values go from 0, which is dark purple, to more than 35 meters, which is yellow. It's safe to assume that zeros are actually the lack of any trees. So we will, in the next step, turn these zeros into NAs and essentially get rid of them. Replacing values using Terra is straightforward. We can just use the if-else function from this package. And then in this process, I will be creating a new object, simply because I don't want to replace this existing one and go through the entire process of again downloading the file. So within this if-else, what we can say is, first of all, provide a condition. So if this raster that we downloaded equals 0, simply turn it into an NA, otherwise keep the existing value. So if you use Terra to plot this newly created raster object, you will now see a more realistic picture where we got rid of all the values that were equal to 0, essentially places without trees. And what we have now is only those raster points where we actually have a certain tree height. We're slowly getting ready to create our map, but one thing that you probably noticed so far is that we cannot really pinpoint what are the areas of Oslo that have certain tree height. This is why we will fetch the street tiles data, which is gonna help us incorporate this information and map it onto specific areas. So before we can actually do that, we first of all need to provide a bounding box for the area for which we want to get the tiles. So the easiest way to do this is simply use the function for creating bounding box from the asset package, and then create the bounding box based on the city quartz object. So this is the first thing that we're going to do. The second one is to get the actual tiles using map tiles. Map tiles has one convenient function, which is called get tiles. And then over here, what we will pass as the first object is this CDB box, or the bounding box. So this is the bounding box of Oslo once more. Then in terms of the provider, this is what are the tiles, what is the provider that you're going to get tiles from. And if you actually are using VS Code like I'm using, and you hover over this specific function, and then you scroll down, you will notice here there are a lot of providers. The one which is the default one is OpenStreetMaps, but we will be going in this tutorial for a bit different one, and that is CartoDB. So CartoDB, we will go first of all for the dark one. So it's called CartoDB Dark Matter. So I'm just gonna copy this one and I'm gonna put it here. And of course you need to declare it as a string. Now, once you do that, you also need to create here a zoom level. If you were working with OpenStreetMaps, you understand the higher the zoom level, actually the more detail you get the map. So it actually zooms in. Now, because we're working with a specific part of Oslo, we definitely want to zoom in as much as possible. So I choose here a zoom of 15, but of course you can experiment depending, of course, on your area size. The next thing I want to declare here is that I want to crop the image or these styles only for this specific zone. And again, one last thing is I don't want to reproject this data. Once again, we can visualize this image that we got, this time using plot RGB because we have an image with reds, greens, and blues, and over here simply passing the street object. Over here you will see a very, very dark background with labels and also the street view for this extent of Oslo. In order for us to be able to visualize this raster file with ggplot2, we first of all need to turn it into a data frame where we will have 3 columns. One is going to be longitude coordinates denoted with X, then latitude coordinates denoted with Y column, and finally the third column will be the value, which in our case is the tree canopy height. So let's first of all create a data frame, and then let's turn into a data frame this newly created cdchm new, and very importantly here, let's declare that this one is gonna have X and Y coordinates. All right, once we do that, what we can do is we can inspect this newly created object and just see what are the actual names of it. So you can clearly see here it has 3 names. So it has, as I said, X, Y, and the third one is the value. Now here it inherited the name from its previous object, raster file. So what we can do is simply change the names of this third one like this. So we put here in the brackets 3 to denote the third column, and over here we can simply put, for example, CHM. One of the prerequisites in creating a map is to declare first of all the legend breaks based on your data, and then also the color palette. Let's start off with breaks. You probably remember that at the very beginning, I installed a package which is called class int, and then this package has a function class intervals, which is going to help us use natural intervals to create a legend breaks based on our data. The first thing we need to do here is to define what we are going to use from this data frame to define. Of course, we're going to be using this CHM column from our data frame. The second argument is how many breaks do you want to have. I usually go for 4 to 8. So here I'm going to go for the middle ground, which is 6. And then finally is the style which you're going to be using. I'm going to here use equal spacing between or among these different breaks, but you can also check there are even more different types. And then the final thing is, because this breaks object is going to be a list, it's important that you take a specific element here, breaks, which are going to be exactly those breaks that you just calculated. Now the second step here is to define the color palette, and over here again we'll be using HCL colors from base R to do that. The first thing is that we need is the number of colors. So the number of colors here should correspond to the number of breaks. So I'm taking here length breaks, meaning it's going to return only that number that corresponds to the number of breaks. The second is the color palette that you want to do. And then if you actually check the HCL colors website, you will see there are many of them. We'll be using one of them. It's called AG underscore and then green yellow. Essentially, this one combines green and yellow in a very appealing way. And then the last one is whether you want to reverse this palette. Now, let me tell you how this is going to look like. If you don't reverse this palette, we'll simply have lighter colors representing higher values in our data, and then darker colors representing lower values in our data. So we don't want to reverse this order because we are working with a night mode map or a dark map. If we are working with a light map, then we would reverse because it's more intuitive on a light street view map to have higher values in darker colors and lower values in lighter colors. So again, we're using here a dark map, but I'm also going to show you how you can create a light map as well. And we're finally ready to create our map, so let's get to it. We'll be using, of course, ggplot2 from tidyverse package. And over here, we will first of all define our main data. So our main data is this data frame file, which has information on the tree canopy height. Now, the second one is adding that street view layer. And again, we'll be using tidyterra for that purpose. So geomspat raster RGB makes sure that we can plot images together in ggplot2 with the help of tidyterra. That's why I'm using this. The only thing you need to do here is you need to define here data is streets. Now, one thing to keep in mind if you want to make this layer crisp is to declare also what is the maximum number of cells that tidyterra is going to plot here, and how do you actually know what is the maximum number of cells. So what you need to do here is you need to inspect quickly this streets object, just like I did, and over here you will see dimensions. So dimensions are 1.6k, 1.7k by 1 also 0.7k, something like that. So if you actually go then over here to your editor, and if you paste these two values, and then if you multiply them, all right, and then show here the output in R, you will see here that this is something around 3 million cells. So you actually need to declare here in your tidyterra code that the maximum number of cells is around 3 million. So in R, if you want to declare that, so you just say here 3E6, which means 3 and then also 6 zeros following 3. So this is 3 million. This is going to make sure, again, that your street view layer is crisp. Otherwise, if you don't leave this, the tidyterra is going to give it a much smaller number of maximum cells, leading to a very blurry street map view. So this is one small trick that I wanted just to share with you. All right, we can then go ahead and add our, of course, main layer, which is the tree canopy height as a raster. So this is the main aesthetic. So here we need to define that. It has three main aesthetics. So it has X coordinates, Y coordinates, and of course it has the fill argument, which is how are we going to fill this? So we're going to be, of course, filling this with tree canopy height. We can now continue adding more customization to our plot. One of the things that we want to do here is define how the colors will be added and breaks as well. So for that purpose, we can use scale fill gradient. The reason why we're using scale fill here is because our main aesthetics, of course, fill. Over here, we can define several things. One of them is, for example, our legend title. So for the legend title, we can, for example, use tree canopy heights, and then here we can just put meters, or we can just use, for example, canopy height as well. It's the first thing. The second thing is we can define our colors, and we of course have the object under the same name where we store our colors. Then we also have breaks, and we also defined previously breaks. And you can also have labels here. I think labels are very important because our breaks are in decimal format. So here we want to make sure that we declare for our labels rounded breaks. And here I rounded to 0, meaning there are no more places behind the decimal one. All right, so that's the first thing that we can customize. We can, of course, customize our legends. For that purpose, you can use guides here. So for guides, you want to make sure that you declare here guide color bar. And you are defining here guide color bar because our legend is based on the data which is continuous. Okay, so over here, what you can do is you can define several things. One of them is, for example, the direction of your legend. For example, I would like the legend to be horizontal, and I would also like this legend to be on the top. So I can also define that later on. Now, one thing that you can also do here is you can define how high your bar is going to be. And again, we can use here units. And for example, I can go for, let's say, 2 millimeters. I'm opting for this one because we have a horizontal legend, so I want it to be thin. Now, apart from this, you can also define bar width. And over here, you want to make sure that, again, you use unit here, but you want to make sure that you are going for something a bit longer, right? So the bar width is going to be longer. And let's say, for example, we're going to go for 30 millimeters here, which is 3 centimeters. Of course, you can also put here that these are the units so that there is no confusion at all what you are actually doing here. Apart from these things, you can also define, for example, the position of your legend title. So as I said, this can be on the top. You can also define here, for example, label position. So this is going to be for those numbers. Labels can maybe come below the legend key, so they can be positioned at the bottom. You can also horizontally justify your title. So you can, for example, put 0.5, so this would be the middle, 0 would be left justified, and then 1 would be a right justified. You can do the same thing for the labels, so you can do also the horizontal justification. You can also put them into the middle. Okay, apart from these things, you can also customize the theme. So this is how the plot itself is going to look like. And what I like usually to do is use this theme void, which is going to get rid of any excess information around it. And then I like also to use an additional argument here, which is theme, which is going to help me actually customize further some things. For example, one of the things that I want to customize, as I said before, is legend position. So I would like the legend to be on the top. You can also choose some of other sides as well. Another thing that I would like also to customize here is a legend title. And here you need to tell ggplot2 that this is actually text. So you need to declare it here as a text. And after you do that, only then you can actually do some things like this. For example, you can define, what is going to be here, the size. You can also define the color. As we know, the background is going to be dark, it's going to be black. So maybe we can use here the white color. The same thing you did here for the legend title, you can also do for the legend text. And basically it's the same code, except for this small part where you need to say it's legend text. One thing I'm going to change, I would like the legend text to maybe have like a smaller font than the other one. Okay, so these are some of the things that you can, of course, do. One also thing that you would probably like to consider here is the legend background. Now, for the legend background, the default one is white, but because we have here a dark background, we definitely want to make sure this one is also black. So legend background is a rectangle, so we also need to declare it here. And then here what we want to do is say that the fill equals to black, for example. All right, and then this is going to be also reflected here. You can also, for example, do the color, but you can also get rid of the color. So for example, you can put here that the color is NA. Okay, and then one of the last things that I like to do is to shrink the margins around the plot. And over here, what you need to do here is define a list of 4 values. So one is the top. So because our legend is going to be at the top, I want to give it a bit more space. So let's say 0.2, and then everything else I would like to decrease a bit. So right hand side, bottom hand side, I also want to decrease or shrink. That's why I'm using here negative values, as you can see. And then also the left hand side, also -1. And then one last thing, what I want to do here is define what is actually here, what is the units that I'm going to be using, so centimeters. So I added 0.2 centimeters, and then I deduced from all other sides 1 centimeter. All right, and here is the dark version of the map. You can see that the values go from 1 to 39 meters and go from the dark values, color values associated with lower tree height to these light values associated with higher values. And of course, you can see here also distribution if you zoom in for different parts of Oslo, overlaid of course with this dark positron type of the street layer map. So this was the dark version of the map for those of you who like the dark mode, but now I'm going to also show you how you can make the light map, especially for maybe your own papers or other research or anything else. So we're going to actually start off from this place where we define the street view layer. We're going to go to the provider, and then instead of this dark matter, we're going to again use Carto DB, but we're going to use a different one. We're going to be using this Carto DB positron. So we can just copy this one, put it here, and we are not actually going to change the zoom at all. So we're going to keep it at the same. level, we don't need to do anything about the raster to data frame, so that can stay the same. Over here with colors, we are going to make a change. So we're going to actually reverse here the values so that higher values are now associated with darker values and lighter values are associated with lower values. Once you actually do that, we can slide down to the map section where we created our map. So over here, we can actually just go down, and then for the legend title, we can now change here, for example, into black, because the background is also black. And also for the legend background, we don't need black anymore, it can become white. And this is the light version of the map for those of you who like that option. As you can see, we reverse the legend scale, so we now use a lighter color values to associate with lower values, and then darker color values to be associated with higher tree canopy height levels. You can of course zoom in, and then you can also see here with also very high detail, not just a street view map, but also these different points. I will also provide the code for saving this map with ggsave in the description box below. And then sometimes it's useful to export these maps into an HTML file so that you can maybe embed into your own website or share with the wider audience. So I'm going to show you how you can then turn this data into interactive map in Leaflet and then also save it as an HTML file. So I'm going to call this object map interactive, and then from Terra we'll be using a function which is called plat, and it's used for plotting Terra raster files in Leaflet. So the first argument here is x, which means what are you going to use this to plot for. So I'm going to be using this new object where we got rid of this NA values. That's the first thing. The second one is the colors. So I'm going to be using the same colors as we used before. And then here for the alpha value, I would like this raster file to be completely non-transparent. I would like it to dominate the landscape wherever, of course, it's present. And then over here, we can choose tiles. Now, compared to our previous option where we used map tiles, we could use a lot of them, but over here we can only use 3. So I'm gonna go for the streets option, and the streets option in this case, it's basically OpenStreetMaps. So that's the streets option. Now, there are also some other things, such as, for example, what is the number of cells. Now we know from the previous example that we need at least 3 million cells, so we can also define it here. And then also you can define here where your legend is gonna be situated, and I'm gonna go for the top right option. Other options are bottom right, top left, and bottom left options. Now, if you want this immediately visualized, then you didn't have to create a map interactive object, but because I want to show you how you can save this file locally, then I will go with another step. So over here we'll be finally using HTML widgets package, and this one has an option which is called save widget. So over here we simply specify that we want to save the local HTML file using this previously created object, and then we also here specify what is going to be the file name. So we can, for example, call it Oslo CHM, and then here we also need to provide the extension, which is going to be HTML. And very importantly, at the end, you also need to declare here that this is not going to be a self-contained file, so you need to declare that it's false. And this is the interactive map that we created using the OpenStreetMaps as the base map, and then overlaying with tree canopy height. Now, the choice of colors is a bit unfortunate here because the OpenStreetMap layer already has a lot of greens, so maybe in one of your iterations you can definitely change this. But you can also see that in the upper right corner there is also a legend, so you can also track what is the tree canopy height, but in a way more interactive mode. Alright, this is all for today, folks. In today's tutorial you learned how to download a very crisp tree canopy height data from Meta and the World Resources Institute, then how to get it into R and create some powerful data visualizations. If you would like to replicate today's analysis, I prepared the link to the GitHub repo in the description box below, so do check it out. Feel free to clone it, reuse it, modify it as you see fit. If you have any questions comments, or just general feedback, feel free to reach out to me here on YouTube, but also on Instagram and X. If you're new to R and you seek to expand your data visualization and GIS knowledge with R, I've prepared a few cool tutorials for you, so do check them out. See you next time.